Welcome back to the deep dive. Today, we are really taking a big jump into the foundational mathematical structure of materials thermodynamics.
hmm
If you think about the first and second laws as these, grand philosophical statements, what we're doing today is getting into the operational rules.
We're making it practical.
Exactly. How do we actually establish criteria for equilibrium in systems we can control in a real lab?
That's it. Our mission today is, well, it's highly pragmatic. We're starting with that core relationship, the combined first and second laws for a simple, closed system.
Which gives us the change in internal energy.
Right, the familiar du equals TdS minus PDV.
And, we immediately hit a wall with that. The equation itself is perfect, mathematically, but its independent variables, entropy, S, and volume, V, they're just so inconvenient for a working scientist.
Deeply
You
inconvenient.
can't just walk into a lab and, dial up the entropy of your system. It just doesn't work that way.
Precisely. So we need criteria for equilibrium that depend on variables we can easily measure and control. Things like temperature, T, and pressure, P.
The things you actually have knobs for.
Exactly. And this necessity, it forces us to introduce a whole family of what we call auxiliary functions or thermodynamic potentials. They're designed specifically to swap those awkward variables for useful ones.
Okay, so let's look at how we actually create these functions. We can start with the one most people see first, right? Enthalpy, H.
Yep.
We define it with a pretty simple transformation. H is defined as U plus PV. So what do we gain by just tacking on that PV term?
Well, by adding that term, you're essentially changing the natural variables of the function. When you take the full differential and you substitute in our equation for du, you find that for a simple closed system, dH is TdS plus VdP.
Okay, and the physical meaning.
The physical meaning is key. If you hold the pressure constant, that VdP term it vanishes.
And there's the insight. At constant pressure, the change in enthalpy, delta H, is just equal to the thermal energy going in or out of the system.
Yet the Q sub P.
It's literally the heat function, but only under constant pressure conditions. And now our natural variables are S and P.
Exactly. So moving on, the next potential helps us understand work. This is the Helmholtz Free Energy, which we call A.
It defined as A equals U minus TS. So here we're subtracting the entropic energy term.
We are. And the physical interpretation here is, well, it's crucial. A measures the maximum total work a system can perform during a reversible isothermal process.
Isothermal means constant T. And if we also hold V constant, this gives us our criterion for spontaneity. A has to decrease.
It must decrease, so delta A has to be less than 0 for a spontaneous process.
And that decreasing potential is what drives the system towards
Equilibrium. Equilibrium is reached when A hits its minimum possible value, where dA equals 0. This function, it governs systems like, say, an internal combustion engine, or really anything held at a fixed volume and temperature.
You can almost visualize it, can't you? The minimum of A is this balancing point. The system wants to minimize its internal energy, U, but it also wants to maximize its entropy, S.
And A finds the sweet spot. It's the point where those two opposing drives, U and TS, are perfectly balanced.
Which brings us to, the function that really rules the world of material science, the Gibbs Free Energy, G,
The gold standard.
defined as G equals H minus TS. And it's so important because virtually all material synthesis, processing, testing, it all happens at constant temperature and constant pressure.
And that combination, constant T and constant P, is what gives G its incredible power. Its change, delta G, dictates the maximum non-PV work you can get out of a process.
So things like electrical work from a battery.
Exactly. So if a phase change can happen or a reaction can occur, it absolutely must drive G down.
So if we're in the lab controlling T and P, the condition for any spontaneous change is always that G decreases. Equilibrium is when G hits its absolute minimum.
Where dG equals 0. We've successfully traded our inconvenient variables for the ones we can actually use. Yeah. So now that we have these four potentials, U, H, A, and G, we can formalize their structure. These are what we call the four fundamental differential equations for any closed, simple system.
Okay, let's lay them out.
First, du equals TdS minus PdV. Its variables are S and V.
Right.
Second, dH equals PdS plus VdP.
Right.
Variables are S and P.
Yeah, okay.
Third, dA equals minus SdT minus PdV. Variables T and V.
And finally, the big one.
And finally, dG equals minus SdT plus VdP. The variables are, of course, T and P.
And just looking at those, you see these really clear mathematical patterns. Like in that dg equation, the volume, V, is just the partial derivative of g with respect to p at constant t.
The structure itself tells you how the variables are linked. It's beautiful.
But this all assumes nothing is changing chemically.
That's the catch. As soon as you allow for chemical reactions or phase changes or, open systems where material can come and go, we have to expand our equations. We have to introduce the concept of chemical potential.
The symbol mu. So how does that fit into our G minimum criterion? If G has to minimize, adding a new term for composition change has to sort of respect that principle.
It does. It fits perfectly because we define the chemical potential of a species, we'll call it mu I, as the partial derivative of G with respect to the number of moles of that species, Ni.
So mu I is the partial of G with respect to Ni, holding T, P, and all the other species constant.
Exactly. Physically, you can think of it as the incremental change in the system's energy when you add just a tiny bit more of species I while keeping T and P constant.
So it's like the energy cost or maybe the energy gain associated with changing the composition.
Precisely. And this allows us to write the complete fundamental equation. Let's focus on the Gibbs function. dg now equals minus sdt plus vdp plus the sum of mu I d and I.
And that final term, the sum of mu I d and I.
We often call that chemical work. It's the work associated with changing the composition of the system.
And the power of thermodynamics is its flexibility, right? If you're dealing with, say, a magnetic material, you just add another work term.
You do. For the dg equation, you just tack on a term like minus mu naught Vm dh, where m is magnetization and h is the magnetic field. It's this beautiful, expandable framework.
Okay, let's pivot to the tools that really connect these theoretical definitions to what you can actually do on a lab bench, the Maxwell Relations.
Right, so because U, H, A, and G are all state functions, their differentials are what mathematicians call exact. And this property is our secret weapon.
The main value here is what?
The main value of the Maxwell Relations is that they mathematically guarantee that things we can't measure. And that's usually derivatives involving entropy, S, can be figured out just from derivatives of things we can measure, like P, V, and T.
Let's use that dg equation again as an example. dg equals sdt plus vdp. What's the Maxwell relation that falls out of that?
The resulting Maxwell relation is that the partial of S with respect to P at constant T is equal to the negative of the partial of V with respect to T at constant P.
So what does that mean in, plain English?
It's a beautiful relationship. It means that the change in a material's entropy, when you squeeze it, that's directly tied to how much that material expands when you heat it up.
Yeah.
So if a material expands when you heat it, which most do, then increasing the pressure on it must decrease its entropy. The math just forces that connection.
It connects these two seemingly separate properties.
It does. And we use these relations to derive what are called the TDS equations. These are pivotal because they let us calculate changes in entropy using measurable things like heat capacities and expansion coefficients.
The second TDS equation is probably the most useful one since it uses T and P as the variables.
It is. It says TDS equals C P dt minus T times the partial of V with respect to T at constant P, all times dP.
And that shows us exactly how entropy changes with temperature through the heat capacity term and how it changes with pressure through that thermal expansion term.
And this framework also provides a really fundamental explanation for something we always observe.
Which is
that the heat capacity at constant pressure, Cp, must always be larger than the heat capacity at constant volume, Cv.
That's a key insight. The difference, Cp minus Cv, is proven to be proportional to a bunch of terms that all have to be positive. So the difference has to be positive. But why, physically?
Because when you heat a system at constant pressure, some of that energy goes into raising the temperature. That's the Cv part. But, and this is the key, additional energy is required for the system to expand against that external pressure.
So Cp has to account for that expansion work.
It has to, and Cv doesn't. So Cp is always bigger. So now for a couple of fundamental applications that really highlight the power of this whole mathematical structure. First, the behavior of an ideal gas.
Okay.
Using the Maxwell relations, we can derive what's called the internal energy equation of state. It's that the partial of U with respect to V at constant T equals T times the partial of P with respect to T at constant V minus P.
That sounds complicated, but if you plug in the ideal gas law, P equals RT over V.
The whole right-hand side just simplifies to zero.
Which is a huge deal. What does that prove?
It proves rigorously that for an ideal gas, the internal energy, U, is completely independent of its volume. You can expand an ideal gas isothermally Its internal energy doesn't change.
And you find a similar thing for enthalpy.
Yes. Similarly, we find that the enthalpy H of an ideal gas is independent of pressure. This is the mathematical reason why, for ideal gases, we often say their energy is only a function of temperature.
Okay, what's the second big application?
The second one is essential for any experimental thermodynamist, the Gibbs-Helmholtz equation. This equation is the bridge between the change in Gibbs free energy, delta G, and the change in enthalpy, delta H.
And the relationship is?
It's that the partial of delta G over T, with respect to T, a constant P, is equal to minus delta H over T squared.
Why is that so powerful?
Because you can run an experiment. You can measure an equilibrium constant over a range of temperatures, which gives you delta G. Then you can just use the Gibbs-Helmholtz equation to calculate the enthalpy change of the reaction, delta H, without ever picking up a calorimeter. It's an absolutely indispensable tool.
Let's end with a really cool physical application of these cross-property relationships, the magnetocaloric effect.
Yes.
This is an indirect effect that comes from the Maxwell relation connecting entropy and magnetic field. So how does this abstract derivative actually create a cooling effect?
It all comes down to manipulating entropy. First, you apply a really strong magnetic field, H, while keeping the temperature constant.
Isothermally.
Right. This forces the magnetic spins in the material to align, which decreases the magnetic entropy. Since the whole process is isothermal, the system has to dump that excess entropy as heat into its surroundings.
Okay, so spins align, heat gets removed, temperature stays constant. Got it.
Then you isolate the system so no heat can get in or out,
Adiabatically.
and you remove the magnetic field. The magnetic spins immediately want to go back to their random high entropy state. But since the total entropy of the system has to stay constant, the increase in spin entropy has to be perfectly balanced by a decrease in the thermal entropy of the lattice.
And decreasing the thermal entropy means?
The temperature of the material drops, sometimes significantly. That's magnetocaloric cooling, a direct consequence of a Maxwell relation.
So let's bring it all together. What does this all mean for you, the listener?
We started with the mathematical inconvenience of using entropy and volume. And through these Legendre transformations, we defined 4 fundamental thermodynamic potentials, UH, A, and the really indispensable G, the Gibbs Free Energy.
And we established that the criterion for equilibrium, especially for reactions and phase stability, it all boils down to finding the minimum of the Gibbs Free Energy when you're working at constant temperature and pressure.
And the real power of the Maxwell Relations and the TDS equations is that they transform this whole theoretical framework into a measurable, usable science. They connect theory to the lab bench.
And as a final thought for you to mull over, the fundamental math actually constrains the physical world. Remember that relationship we found? The one connecting the curvature of the Gibbs free energy with respect to temperature?
Yeah, the second derivative. The partial squared of G with respect to T squared at constant P equals minus Cp over T.
So, because heat capacity, Cp, must always be a positive quantity,
Which it must.
this equation proves that a plot of Gibbs free energy against temperature has to always curve downward. It must always have a negative curvature.
The mathematics fundamentally defines the shape of stability. It's not an accident, it's a requirement.
A perfect encapsulation of how these fundamental equations govern everything we observe. Use this framework as your core map as you go on to explore reactions and equilibria. Thank you for joining us on this deep dive.